Okay, so I guess we'll start. So hi guys, this is Kailash, and today we are gonna do some deeper topics in Linux. So basically, today it'll start with the continuation of the previous class on not on Markov chains, the probability class. If you people have attended it, and I'll do a little bit of topics related to that. I'll start with that. And we'll go on to some new and exciting topics such as like e-power matrix. We'll be covering what that means and how that even came to be, where that's applied, stuff like that. And we'll be covering one or two more topics in between, which let's see as we get on with it. Okay, so first topic, eigenvalues. So the last lecture we had Markov chains. So what were Markov chains? Markov chains were special matrices. In Markov chains, we would have come across special matrices which would like explain how different events occur and how the probability would change accordingly. So you would have a vector representing all the possible outcomes, and you'd have a matrix explaining how those outcomes depended upon each other, the probabilities. And after a long time, if you want to calculate the probability, you would raise that matrix to the power infinity. You take the limiting power and you would um, find the final probability by multiplying the matrix with the initial probability of events. So that we had to do something to the power infinity. So we'll we for that what we would have done is we would have used eigenvalues and eigenvectors. So yeah, that's where we are going to start it today. So what is eigen? Eigen is the German word for characteristic. So eigenvalues is basically, let's see if I have the slide. Yeah. So in maths, there are some vectors that characterize a matrix, and there are some values which characterize a matrix. And given these two, we can like basically describe any matrix almost fully. So these vectors are called as eigenvectors, and these are quite special. It is found that these vectors obey the equation ax equals lambda x. So how this came about, we'll like talk about it in some time. And if you think about a matrix in the geometrical way, these vectors they simply get scaled by the transformation that the matrix represents. So a matrix maps every vector to every other vector, and eigenvectors corresponding to a matrix, they basically get scaled. So if it initially had a magnitude 3 and some direction along n cap, it would still have the direction along n cap, but its magnitude would be some 6 or 7, say. Its magnitude would change, but its direction would not change. So that is a property of eigenvectors. Um, Now, the equation we had was ax equals lambda x, and this number lambda, it explains how the eigenvector gets stretched or shrunk. So it is a characteristic of the eigenvector and also a characteristic of the matrix, and these lambdas are called the eigenvalues or characteristic values. These numbers, in a way, if you want to like convert a matrix into, say, if you want to use a matrix somewhere in equations like a polynomial or something, instead of writing the matrix as such, eigenvalues help us to represent the matrix as a number. So that's how they came into picture. You didn't want a matrix because a matrix is this huge bulky mass of like, I mean, multiple elements, and it's a very complicated object in general. So basically, eigenvalues convert this matrix into a number, a single number which you can control. I mean, not a single number because there are multiple eigenvalues, but they help in converting like that complexity into something a bit more tractable. So yeah. So next, we got an intro to these eigenvalues and eigenvectors, but how do we obtain them? So that's where we start with. And eigenvalues and eigenvectors, the first thing that you should always remember is the equation ax equals lambda x. So lambda is the eigenvalue, and any vector x that satisfies this is an eigenvector. So for an n cross n matrix, you would have an eigenvalue as a number and an eigenvector as n elements. So we'll talk about only we're assuming square matrices. I think that is worth mentioning. So how do you find eigenvectors and eigenvalues? You take the equation ax equals lambda x, you transpose the lambda x to the other side, and you basically get a minus lambda I times x equals 0. You can do this because of distributivity. We would have talked about it in the first session. Now, now comes the interesting part. So you have a minus lambda I x equals 0. So now you basically want to show the determinant is 0. So you have a vector, you multiply that, like you make a matrix act on it, and you get 0. And you obtain that the determinant is 0. Now this is slightly non-trivial, but basically this arises from the fact that if you have any equation a minus lambda I times x, you obtain that the columns of the matrix are not linearly independent. So in order to explain what I mean, so if you take the equation a minus lambda I x, what are you basically doing? You're taking every row and you're multiplying that by like constants, right? And you get some linear equations, and all of those equal 0. Now the thing is, every column is multiplied by the same constant, right? So if I were to add all those equations together, I would still get 0. So let me take a 2 by 2 matrix A, B, C, D. I think it would help if I could write things down. Okay, never mind about that. I think there's a problem. Fine. So let's take a 2 cross 2 matrix. So you have 2 rows and 2 columns. Now you take a vector containing 2 elements and you multiply the matrix by the vector. Let's say the vector is 1, 2. If you observe, you'll get 2 linear equations, right? So the first row of the matrix gets multiplied by the vector. So first element multiplied by first element of the vector. Second element of the matrix multiplied by the second element of the vector. And that equals 0. Similarly, you'll get second row first element multiplied by the first element of the vector equals 0. Second row second element of the matrix multiplied by the second element of the vector, that equals 0. So you get another equation. Now you add those two equations together. So which element is the first element of the vector multiplied by the 1? The 1 is multiplied by the first column of the matrix, 2 cross 2 matrix. So if you have the matrix A, B, C, D, you get A plus 2B equals 0, C plus 2D equals 0, A plus C plus 2 times B plus D equals 0. So that basically means you have, you basically have the first column multiple. So you have the first column multiplied by a constant, and second column multiplied by another constant, and so on, and the sum of all those equals 0. So and from these n equations, you can figure out in a similar fashion. I'm not explaining the entire process, but I've tried to motivate it that the rows or columns of the matrix is not linearly independent. You can show it. Maybe if you have doubts, maybe after the session we can look at the process. And that basically gives the fact that the determinant of the matrix is 0. So another way is geometrically. So a matrix is like a shifting or scaling of various vectors, and only if the determinant is 0 can you scale a vector by 0, basically. So if that helps in motivation, you can take that kind of interpretation to geometrically. So yeah, that is an important thing. Now you have determinant of a minus lambda I equals 0, and that is an equation. Right, it is a polynomial equation. It is not a matrix equation. It has numbers in it. And you're solving for lambda. So you basically get all the values of lambda for which determinant of a minus lambda a equals 0. And these lambdas are the eigenvalues of the matrix F because they will satisfy ax minus lambda x equals 0 for some x. So that also has to be shown, proven, but I'm not proving that right now. You can look up the proof. I think it's easy. So you have determinant of a minus lambda equals 0, and solving that you get all the values of lambda. And how do you get all the values of x corresponding to it? You back substitute. You take the equation ax equals lambda x. Now you have the values of lambda, and you basically put in the value of lambda, and you get in the value of x out from the equation. You get a couple of linear equations which you need to solve. You have n variables because x is a n element matrix, so a vector. And from that you get x, and you get an eigenvalue and the corresponding eigenvector. That's how you solve it. Now, there's also one more interesting point. So if you take the determinant of a minus lambda equals 0, you get a polynomial equation, right? But it turns out that the matrix itself satisfies the equation. So what do I mean by that? So let's say you have the equation x square minus 2x plus 1 equals 0, x minus 1 whole square. So if you take some matrix A, what is A square? A square is A multiplied by itself. Multiplication is defined for a matrix. Minus 2 times A plus 1 or some constant becomes a constant times the identity matrix. So A square minus 2A plus I equals 0. And the matrix, it turns out, it satisfies its own characteristic equation. Now that proof is a little bit involved, but again, it relies on the, again, it can be derived in a similar fashion. You repeatedly apply ax minus lambda x equals 0, and that's how the derivation goes. It's called the Cayley-Hamilton equation. After the session, I think you should look it up. The proof is quite interesting because you write a lot of sums and everything cascades, and you finally get what the polynomial itself. Okay, so moving on. Let's take an example. Right, we've talked theory for so long, and I think an example will help make things better. So let's take a matrix A equals 2, 2, 1, 3, as shown here. So what's the first step? You write A minus lambda equals 0. So they've taken lambda as x in this example and basically written that as a polynomial. So 2 minus x, 3 minus x, and 2, 1, the determinant of this matrix will be 0. So that is basically x minus 2 times x minus 3 minus 2. So determinant of a 2 cross 2 matrix, if you didn't know, is this times this minus this times this. So you basically get that equal to 0. You get a quadratic, and you get the eigenvalues as 4, 1. Now, you put in a minus 4 is 0. You solve it. The way they are solving it is the way you solve linear equations. This is something I think you would have covered in the first session while covering RREF and stuff. So you solve it and you get two eigenvectors, and you get the eigenvalues and eigenvectors correspondingly. Now, what is interesting is if you think about it, like you basically have four numbers, and to me, it's like it strikes me interesting because as very interesting that only two vectors in the entire space get scaled, as in 1 and minus 2 1. There is some theory indeed behind. It could be less than 2, but I think we'll cover that in a bit. But the fact that it's at max 2 is actually quite interesting. I mean, think about it. There's like an infinite spectrum of vectors. Even if you take up to magnitude, if you take all the vectors in a unit circle pointing towards a point on the unit circle, you see that there's so many vectors, right? Why is it that just two have to get scaled? I think that's extremely interesting, right? So yeah, let's move on. So now we come to some properties of the eigenvalues and eigenvectors. So first property, the product of eigenvalues is the determinant of the matrix. What matrix are we talking about? We're talking about the matrix A. And so how does this come about? Right. It comes from this equation. Determinant of A minus lambda equals 0. So if you look at this question, the way they've written it is basically in a factored form. So you basically have this equation xi minus a equals some factoring, and you want to put x equals 0 in this, lambda equals 0. So what do you get? Determinant of a, determinant of minus a, which is determinant of a because you only like care about the absolute value. And on the right side here, you get 2 times 3, which is 6 basically, right? 2 times 3 minus 2, which is 4. And if you factor this out completely, you get x minus 1 times x minus 4, right? And the product of the eigenvalues like 4 and 1 is what you basically get in case you put x equals 0. So the determinant of A is when you put x equals 0, and when you put x equals 0, you get the constant term, which is the product of all the equations of the polynomial. So you get the product of the eigenvalues is the determinant of the matrix. That's the first property. Second property, the sum of the eigenvalues is the trace of the matrix. Now that proof is slightly more involved, but um, it turns out that in fact, I don't exactly recall the proof, but it can be proved that the sum of the eigenvalues is the trace of the matrix. So here, let's take this example itself. The matrix is 2, 2, 1, 3. So we expect the sum to be 2 plus 3, which is 5. And what is the sum of the eigenvalues? 4 plus 1, and which is also 5, right? So in this example, it clearly works. And similarly, it also works for every other example you can think of. Third one's very interesting. So if lambda is an eigenvalue of A, then lambda power x is an eigenvalue of the matrix A power x. So the way you do this is basically in a similar way to the way we derive it. So you take this equation, the way we derive the eigenvalues themselves. So you have ax equal to lambda x. Now let me pre-multiply. Again, multiplication is not commutative with matrices. So let me pre-multiply with the matrix A itself. So I get a square x equals a lambda x, but the lambda can come out because it's a constant, it's not a matrix. So a times lambda is lambda times a. Scalar multiplication is commutative. So lambda times ax, but what is ax? Lambda x again. So it's lambda square x. So a square x equals lambda square x. Now pre-multiply a again, you get a cube x equals lambda cube x. So in general, you get a power x corresponds to lambda power x, or rather the eigenvalue of a power x is lambda power x if lambda is an eigenvalue of, right? So Audrey, I think it's time for a poll. Do you think eigenvalues can be complex for real matrices? I wanted to think about how we derived it, the polynomial we get, and yeah, yeah, okay, nice. The poll is up. Right. People, there are 4 people who think the answer is yes. 5. Is there anyone who thinks the answer is no? I mean, you have real entries everywhere. Where does complex numbers even occur? And why should there be a complex number? As in, it could also be that the eigenvalue simply doesn't exist. We don't need to include complex things at all. Fine, okay. I think we got some answers at least, some 7 people. Right. So the thing is, an eigenvalue is anything that satisfies the equation, and we've basically shown that we basically proven that. So yeah, the answer is yes. Eigenvalues can be complex because the characteristic equation could have complex roots. So that's the thing. And we include complex values because they occur a lot in real life. For example, in while solving circuitry and circuit related problems, we use like characteristic matrices to help in things, and in them the matrices like many a times do have complex eigenvalues. Right. So moving on. Okay, Athreya, second poll. So I mean this is more of a question. So eigenval vectors of A power n and A transpose. A power n we've already covered. Sorry, A power n we've covered the eigenvalue. What would be the eigenvector? And A transpose, what is the eigenvector? Okay, so we'll make a simple poll. Do you think it's some constant times the eigenvector, or do you think it's the eigenvector multiplied by some matrix, or what do you think it is? Athreya, can you put a poll? Athreya? Fine, okay, so okay. So what I mean by power is basically if V is an eigenvector, then it's some A times V. So A transpose is, I don't know what it is, but if it's A power n, maybe it's A power n minus 1 times V or something and stuff like that. Okay, so around 6 people have answered yes, but the like it is a power, but the power turns out to be 0. So the eigenvector, I'm not talking about the value, the eigenvector of A power n is the same as the eigenvector of A. And I'm saying the eigenvector of A transpose is the same as the eigenvector of A. So let's think about how that comes. The way you derive it is again going to this fundamental equation. So Ax equals lambda x, right? And you pre-multiply both sides by A power n minus 1. So the way you get it is A power n x equals lambda power n times x, right? So the eigenvector is still x, but then again you could still in a way say that it's ax or a square x or something, because ax is still some constant times x, right? So in a way you people are correct, but the key factor is that this question is a trick question because both are actually the same thing. It's like if x is an eigenvector, then ax is also an eigenvector for the matrix A. A transpose is quite similar. You derive it the same way by taking transpose on both sides, but it's slightly harder to look at. So for now, I want you to take it as a given, but later you can look up the proof. A transpose will have the same eigenvalue and eigenvector as A. That's the takeaway. Okay, now third thing is A and B share the same eigenvectors only if AB equals BA. Now, in the first session, if you remember, we would have come across the fact that matrix multiplication is not commutative. AB is not equal to B in general. But now that we have eigenvectors, like this is the power of eigenvectors, we can tell a little bit more in general about the properties of matrices. So if AB equals BA, we can automatically say they share the same eigenvectors, A and B. And if A and B share the same eigenvectors, we can automatically conclude that AB equals BA. One application of this is the Heisenberg uncertainty principle. So in quantum mechanics, position and momentum no longer are constants, they are operators of position. So um, momentum itself is a matrix that acts on a 3D vector, for example, position. And in general, it turns out that position and momentum P operated on momentum does not correspond to momentum operated on position. If you've taken a basic course on quantum mechanics, or you will take in the future, maybe you would have come across a derivation. But this derivation basically, you use Cauchy-Schwarz to prove Heisenberg's uncertainty principle. You take the value of the difference AB minus BA. And this AB minus BA is very interesting because in general, a lot of objects don't commute with each other in terms of multiplication. And this object AB minus BA is called a commutator of A comma B. You put it in like the triangular brackets and you call it triangular bracket open A comma B triangular bracket closed. It's called a commutator of A comma B, and this commutator has a lot of properties. These properties are explored in like group theory, and even in quantum mechanics we will explore this. We will use more of the properties. But yeah, Heisenberg uncertainty principle, such a big principle like that, is the fact that it's fundamentally derived from the Cauchy-Schwarz inequality, something that I mean we studied for in JA. It's like, I mean, I was mind blown by it. You can actually go through the derivation. Even I think it is very much feasible to understand the derivation. So that is something you should probably do. So that brings us to the end of eigen vectors. I think we should take the attendance right now. So just give me a second. Adria, can you send the attendance form? Okay. Doubt in YouTube, or oh, had they committed, what would have happened? Okay, suppose if position and momentum had commuted, then you wouldn't have uncertainty at all. If it was equal to zero, you could have derived that the minimum uncertainty in position and momentum would be equal to zero. So position and momentum could be measured simultaneously, and you could talk about position while talking about momentum. Now, basically, the problem here is if you talk about an absolute momentum, you cannot talk about the position of the particle in the same line because both of them don't coexist together. So yeah, I think Adria shared the attendance sheet. I'll give like some 5 minutes to fill it up. We'll restart the session by 11:07. So fill the attendance fast. Fine, okay. Adria, shall I start? Or should I wait for a minute? No. Okay. Fine, okay. So we've done the first part. We've basically done eigenvalues. Now comes the interesting part. So what I've basically given is a tool to unlock, I mean a key to unlock a lot of doors. And one of the doors is diagonalization, which diagonalization is for special matrices, but the power of it is such that you'll come upon a form called the Jordan canonical form, and that can basically destroy, like, I mean, rip apart matrix problems like anything. It's an extremely powerful form. So we won't be covering Jordan canonical form yet, but we will be covering diagonalization. So let's look at that.